Great. Oh, let's get going, shall we? Thank you, Shannon. Thank you all for coming. I really appreciate it. And as she's mentioned, this is my proposal for my thesis, my master's thesis. So I'll be investigating plant species and design strategies that enable the establishment of multi-beneficial habitat in dryland agroecosystems. It's a lot of big words there, but we'll give you an outline of what we're looking at soon. So here, this is what we're looking at today: an introduction, some objectives and questions, literature review, theoretical framework, methods, deliverables, assumptions and limitations. So first of all, how did we get here? Why have we even got this question coming up today? So when pre-European Māori arrived between 1320 and 1350, they were met by a significant number of flightless birds and native bush, and to attain these food sources, forests were burnt, land was cleared to make hunting easier. So this began the long-term removal of original habitat that would continue when European settlers arrived in the 1800s and began setting up farming systems similar to what they had back home in Britain. As more settlers arrived and the population continued to grow, more food sources were required, and agricultural intensification took over. This led to more forests being removed and more environmental degradation. As the balance shifted, there began to be quite a loss of biodiversity and species extinctions. However, because the population was still growing, we still needed to provide lots of food, and one of those ways was obviously through agriculture. Today we're requiring, with the biodiversity challenges out there, we're still requiring that same amount of food. So I propose that we establish multi-beneficial vegetation in dryland agroecosystems. So that's where we'll be heading today. So just a bit of a look at the local context. I'll be looking, the case study site I'll be looking at will be Ashley Dean Dryland Farm. It's in the Selwyn district, south of Christchurch in New Zealand. Population, well, it's growing quite a lot. I'm not sure if you've been here in the last 20 years, but in 1997 it was around 26,000, and today it's nearly 74,000. And more specifically, Rolleston has grown from 1,700 and 1,800 to nearly 25,000 today. So that's quite a significant growth. And I don't know if you can see the image on the bottom left there, but it's a kind of an old photo from the Selwyn Library, but I've outlined Ashley Dean right in the bottom corner, maybe a bit small for you. But that just shows you how the peri-urban context that the farm sits in. And historically, actually Selwyn district's an agricultural region. However, it's changed a lot with a 973% increase in dairy farming between 1990 and 2019. All of this was taking place in an area with less than 1% of original vegetation remaining. So just before we go a bit further, I'll just clarify the definitions that I'll be using. A dryland agroecosystem is the unirrigated agricultural ecosystem characterized by water scarcity and drought issues, and a cool wet season followed by a warm dry season. Multi-beneficial, so in this case vegetation, is a component of the landscape that provides multiple environmental and ecological benefits. So for native fauna, there will be food, habitat, nesting sites, and protection from predation. And for livestock, we'll be looking at fodder, shade, and shelter. Looking at the research objectives and questions now. The main objective is to investigate plant species and design strategies that enable the establishment of multi-beneficial habitat in dryland agroecosystems. To address this, we're looking at three further questions. So which vegetation species provide multiple benefits for native fauna and for livestock? Which spatial design alternatives for revegetation patterns within dryland agroecosystems have the greatest potential for multifunctional benefits to native fauna and livestock? And finally, as water security is a big issue, what are the most suitable ways to harvest or retain water on site to mitigate these drought and water security issues, and also to establish new plantings? So I guess we're looking at what goes where and why. That's kind of the big overarching philosophy that we're looking at here. So the first thing I looked at in the literature review was biodiversity in dryland agroecosystems. So vegetation is essential for life on our planet, and many other things. It provides clean air and mitigates climate extremes, providing habitat for wildlife, sequesters carbon, and provides building materials for construction. However, the development of human societies, including towns and cities and agricultural land use, has driven the removal of approximately 85% of original vegetation worldwide. There are also multiple benefits provided to fauna and livestock. The ones, as I've mentioned previously, are the food, habitat, nesting sites, and protection from predation. And the ones to livestock are fodder, shade, and shelter. So clearly there you can see the importance of vegetation in an ecosystem. Birds were the next element that I looked at. They're a key element in dryland agroecosystems as they provide key ecosystem services such as seed dispersal and insect pest regulation. In addition, many bird songs enhance the landscape aesthetics and provide an enjoyable experience in a landscape. However, of the approximately 9,000 or 10,000 species of birds worldwide, about 1,480, 1,500 of those are threatened with extinction. And the situation is worse in New Zealand, with 40% threatened or at risk. And the main causes of extinction are habitat degradation and predators. Next, looked at invertebrates, which include spiders, moths, butterflies, beetles, earthworms, etc. They are also responsible for pollinating approximately 70% of plants worldwide, with bees in particular pollinating around 30,000 plant species. Invertebrates also provide a valuable source of food for insectivorous and omnivorous birds, and they apparently like to eat quite a lot, about 450 million tonnes a year. So not my idea of a nice meal, but that's fine. If we move on to the next section, we looked at lizards. So there's about 6,300 species of lizards existing in the world today, and of those, relatively little is known about their conservation status. However, in New Zealand, 85% of lizard species are threatened or at risk. Like invertebrates, they're responsible for pollinating plants, as well as dispersing seeds across the landscape and controlling insect numbers. Freshwater species, their habitats comprise less than 1% of the global surface, and they're home to an estimated 126 to 140,000 plant and animal species. Additionally, a significant source of food for humans and wildlife. However, more than 80% of New Zealand freshwater species are now threatened or at risk. And similar again, habitat degradation is a big issue with water pollution and invasive pests. Looked at soil biodiversity. So it's more complex and diverse than above ground biodiversity, with millions of different species existing in any given ecosystem. It's essential for breaking down organic matter, building soil health and quality, and providing nutrients to plants via interactions in the rhizosphere. Organisms range in size from microflora and microfauna, which are bacteria, fungi, protozoa, and nematodes, to mesofauna, springtails, mites, macrofauna, lovely earthworms, to megafauna, so moles and some rodents. And then finally looked at livestock, key element of an agroecosystem, you'd think. Livestock species in dryland agroecosystems include alpacas, llamas, beef cattle, milking cattle, deer, goats, horses, poultry, pigs, a whole lot of them, and sheep. Livestock provides food and fibre for human consumptions and also food for wildlife as well. And traditional farming systems, however, can cause adverse effects on the environment. And we're seeing change in farming systems today in response to this. And one of those is there's a suggestion that replicating a natural system of herd management, as we've seen in some of the African plains and North American plains, may benefit biodiversity and restore environmental health. And a fun fact for you to end the literature review on biodiversity: there's 28 million sheep in New Zealand. So there you go. That's a huge decline from 1982, the early 1980s, when there were, I believe, over 70 million. The next area of literature review was looking at spatial design strategies. So I'll be looking at 5 different strategies for this. And as we go through, I will attempt to focus down onto possibly 3. The first set of strategies were efficiency substitution strategies. They focus on substituting existing features and practices with more environmentally responsible ones. For example, reducing artificial inputs and reducing or making more efficient use of irrigation on farms and replacing those with more responsible ones. However, this may result in green infrastructure, so trees, etc., that's small, fragmented, and unable to support many ecosystem services. You can see many paddocks. This is a kind of, as you go, a sort of a status quo, as you like, slow, steady, slight changes as we go. Next step were biodiversity design strategies. They aim to mitigate environmental impacts of farming and provide additional ecosystem services. And sometimes that includes the addition of new production systems, conservation, and restoration of existing ecosystem services. So if you can see the picture up in the image up in the top right, there's a bit of the brown, if you like, at the top is showing a steady as you go efficiency substitution strategy. And as you move down, the biodiversity gets higher. There's less human involvement and more natural involvement, if you like, and more environmental services provided instead of dis-services. The next one, spatial design strategy that we'll look at, is the ecological connectivity strategy, where you spatially map areas of high and low connectivity, so patches, corridors, etc. And that allows you to prioritize areas that require restoration, or maybe new planting or a new corridor or whatever needs to be done. And one of the cool things is this is used as an ArcGIS linkage mapper tool, and so it can be shared widely online. And conservation agriculture is the next one, which is described by Elizabeth Meyer as creates a multifunctional beauty of a farm. It uses scientific data as a basis for artful design that provides ecological services to the region. So this is a bit more painting on the landscape, if you like, doing nice swirly lines, architecturally beautiful kind of things. However, the desire to create that work of art must be balanced with creating genuine habitat. And the final strategy of messy ecosystems orderly frame, which from Joan Nassau. So in short, nature is inherently messy, while humans prefer tidy and orderly. Providing cues to care demonstrates human involvement in the design. So, and as you can see, the pictures on the right, that doesn't need to be too much of an effort. It could be a mow and strip through a naturally restored area, or a simple rock border around a garden, and that says to people, "Oh, it's not actually messy. Someone's involved. Someone's looking after it. I appreciate that now." So the third area of the literature review is water in dryland agroecosystems, and these are the sources. So water availability is the dominant factor in influencing production in dryland agroecosystems. So precipitation is the primary source of water for dryland agriculture, which means in many areas there are frequent droughts and water security issues if rainfall levels are low. Now, just to quickly show you the amount of fresh water available on the planet, 2.5% is available as fresh water, and of that 2.5%, only 0.3 is available through rivers and lakes. If you're willing to drill a bore down, you can get down to start tapping into that 30% aquifer, start irrigating your dairy farms or whatever you're interested in. But the next thing we looked at is water races, and they are essentially channels that move water from main water bodies or rivers to agricultural land where the water is required. They're also called drainage ditches or irrigation ditches, and they're used around the world, and they're usually gravity fed. The primary losses are through evaporation, wind speed, and channel lining. And the final source of stock water supply. So that provides a source of water for stock that's pumped from a bore, usually stored in a tank, and then distributed across the farm to water troughs. And this can also be combined with domestic use. Look at the methods of retention now. Wetlands. So wetlands have multiple ecological benefits. I can't list them all here, but relevant ones are habitat, water filtration, carbon sequestration. And in New Zealand, wetlands have been a traditional source of mahinga kai, very important. But, however, 71% of global wetlands have been drained since 1900. So that's not sounding too good. So maybe get some more in there. Detention basins. So there's two types of detention basins, wet and dry. Dry basins are more common in dry areas, and provide a location for water to be stored following heavy rainfall or snow events, etc. And dry basins can also be used for paddocks or recreation, a whole wide range of things in agricultural areas. And the sides can be planted with aesthetically pleasing vegetation. However, these retention methods require significant earthworks to form the land into a basin. The next type we'll look at is dams and weirs. So they are constructed across a waterway to retain the flow of the waterway. They can vary in size, with larger dams holding more water for a longer period of time. The water that is retained can then be distributed through channels cut into the sides off into different directions. And soil moisture. So the amount of water that can be stored in the soil depends on several factors, including soil type, presence of organic matter, ground cover, shade, shelter from nearby vegetation. So in general, as we see in the little diagram there, clay soils retain the most water, loam soils the next, and sandy soils the least. However, in practice, most soils are a mixture of all types, so it's important to test the soil at each site. And there is growing evidence also that minimising tillage of the soil can help retain water. So we'll move on to the theoretical framework now, which is landscape ecology. We'll be using a fairly basic or standard theory here. The definition provided by Pickett and Canesso is the study of effects of spatial patterns on landscape components, on ecological processes, and the effects of those ecological processes on those spatial patterns. And the research will use the patch corridor matrix model developed by Foreman. A patch is a relatively homogeneous, non-linear area that differs from its surroundings. A corridor is a relatively homogeneous, linear area that differs from the adjacent land on both sides. And the matrix is the background ecosystem or land use type in the mosaic, which is characterized by extensive cover, high connectivity, and or major control over dynamics. So I'll just introduce the case study site now, which is Ashley Dean Dryland Farm, right about there on the Canterbury Plains. It's about 4 kilometres southwest of Rolleston in the Selwyn district, which you can see on the map on the top right there, and not too far from where we are, or where I am at the moment anyway, at Lincoln University. The cemetery and home blocks make up the 155 hectare dryland block, which is right there. It's been owned by Lincoln University since 1909. Has a history of dryland research in pastures and sheep, and more recently beef. It has low rainfall and freely draining soils, and quite an interesting cultural or social element to the site is there's a historically significant cemetery dating from the mid-1800s, which is why one of the blocks is called the cemetery block. The further methods will be literature review, which seems to be ongoing, and that will just continue through the process to ensure the final document is up to date as possible. There'll be discussions with experts, which again will be ongoing throughout the research process, and will ensure information is as updated and accurate as possible. The discussions will take place with people in the fields of agroforestry, biodiversity, dryland farming, ecology, habitat establishment, water systems, whatever is needed. Discussions will also have approval from the Lincoln University Human Ethics Committee. Further research will involve visiting Te Ara Kakariki green dot sites on public land. This will help gain insight into species, site layouts, and how water contributes to plant growth over time. During these visits, I will take photos and record notes. Then I'll begin an inventory and analysis of the landscape scale. So the bottom right-hand picture is this sort of scale we're looking at of where the vegetation, the habitat patches, the waterways, all that kind of thing are. And that will help identify where the patches are missing, where corridors are missing. And in the long term, hopefully Ashley Dean, the case study site, will be in one of those locations. Move down to an inventory and GIS analysis at the site scale, so at the farm. So this will be identifying the buildings, fence lines, gates, roads, etc., the vegetation that's already there, and then the soil types and a GIS terrain analysis, and formulation of a topographical wetness index through a GIS tool called Saga. And then finally, well not finally, but nearly finally, developing a multi-beneficial species list. So that I'll use a matrix to assess biodiversity benefits that are listed there, and then agricultural benefits, and then we'll somehow get a weighting to include the plantings and the vegetation that are the most beneficial, and provide a list following that. Finally, then we'll develop the spatial plans. So this will be identifying the key components of each of the design strategies that I mentioned earlier, developing some concept plans, so some broad concept plans that are based on each component, carrying out a SWOT analysis on each of these designs, and presenting them. So that sort of comes back to the what, where, why. The what will be a multi-beneficial species list for use in dryland agroecosystems. The where will be a spatial design for vegetation at a case study site. And the why, an explanation and reasoning for the vegetation list and spatial designs. So just move on to some assumptions. Due to the limited amount of time, we're just going to assume that there'll be water available for establishing plantings. That's something that can be looked at in the future. And some of the limitations, obviously we don't need to talk about that one. Time constraints may limit site visits to private land. So I originally had visits to Te Ara Kakarihi green dots on both public and private land. However, at this stage I've decided there's not enough time available to do both. That may still come back in at the end. And being unable to measure, again, the water means there's, unable to measure long-term water rates due to the time constraints. So we're pretty much finished here. There's a timeline of what will be going on. Christmas soon, so that's good. And then a bit of a budget there. So, and finally, I would like to thank these people, Richard, who's in the room here with me. Nice to see you, Richard. But more importantly, Dr. Shannon Davis and Dr. Crowell Dosha for really being patient with me and helping me through this. Mike Bowie, Dr. Colin Merck, Charles Murph, how are you? Wendy McWilliam, I know you're not here, Pablo, and my fellow postgrad students. And I'd like to thank you all for attending as well. I really appreciate that. But most of all, I'd like to thank my wife, Catherine, for putting up with me and for putting up with everything. All right. Thank you very much.
Great. Thank you very much, James.
You're welcome.